This tutorial is entitled Single Frequency AC Analysis. It is designed to complement another tutorial that was called AC Analysis. The other tutorial, the one entitled AC Analysis, is really a frequency response type of analysis. In the single frequency AC analysis, we are concerned with the steady state response to a sinusoidal input at a single frequency. Now I have a circuit here, a simple circuit to illustrate the process, and I've deliberately left these parameters on the right hand side as 0 to make a point, which I'll make shortly when I open up the source. But the actual parameters that I'm going to be using are 100 volts peak for the sinusoidal steady state response at 1000 hertz. Now let's open this up and see why I'm referring to this in the manner I have. All of the parameters down through about the middle are associated with transient response. And I've left all those at 0, although you can certainly put the values in if you so desire. They really don't apply when you do the single frequency response. For the single frequency response, the primary place to enter data is here. You have 100 volts AC analysis magnitude. I could also enter 0 degrees, some other phase angle if I so desired, and some of the parameters down here apply to other types of analysis. But again, for a single frequency analysis, the critical parameter is the peak value or magnitude here, and the data up here have no relationship as far as steady state single frequency analysis is concerned. So let's OK there. And I've listed over here on the left, this is just some listing on the screen. It has nothing to do with the setting here, but I've listed 100 volts peak at frequency of 1000 hertz. Now if one calculates the impedance of the capacitor at 1000 hertz, or 6283 radians per second, for this value of capacitance you will have minus J1000. And since the resistance has a value of 1000 ohms, you have an impedance looking into the circuit of 1000 minus J1000. So that would be 1414 ohms at an angle of minus 45 degrees. So when you calculate the current flowing in by taking the voltage and dividing by the impedance, you get 70.7 milliamps peak at an angle of 45 degrees, plus 45 degrees, since the current flowing into the circuit will lead the voltage at the input. Of course, the voltage on the capacitor will lag the current by 90 degrees. Now, if one makes a calculation of the power in the circuit, the real and imaginary power, or reactive volt amperes, you're dealing with a peak value here, so the RMS value you can determine by taking the peak of the current and dividing by the square root of 2, or you can simply work with the peak value squared and divide by 2. At any rate, the magnitude squared of the RMS current times the resistance will yield 2.5 watts dissipated in the 1 kilo ohm resistor, and we get a Q, that is to say reactive volt ampere value for the capacitor of minus 2.5 bars, or volt ampere is reactive. So these are the calculated values. Now let's see how these values come out when we perform a computation. I'm going to go up to the grapher, click on it, and apply a single frequency AC analysis to it. Now, there are several things you have to enter in the AC analysis. First, you have to put in the frequency, which is 1 kilohertz. I could enter that as 1000 hertz if I so desired. I have two options as far as the computation is concerned. I can have magnitude, phase, or real and imaginary. I'll do real and imaginary first. Let's check and make sure we have the output set to appropriate values. Well, I have a number of parameters here. I have the current around the loop in the circuit. I have the power associated with the capacitor, the power associated with the resistance, the power associated with the source, V in and V out. The two that I don't have in the slot over here are the current through the capacitance and the current through the source. Now, the current through the capacitance would be the same as the current around the loop, or the current flowing into the capacitance. The current on the source would be the same basically, but it would have a reverse convention, so we won't bother with it. So let's hit simulate, and I'll enlarge this. Well, let's go through and look at the various parameters. First of all, we have the input voltage. The real part is 100. The imaginary part is 0 at a frequency of 1000 hertz. We have the output voltage, which for all practical purposes would be about 50 minus J50. And incidentally, the rectangular form is not the best form for expressing voltages and currents, but nevertheless, we can do it that way, 50 minus J50. For the power with the capacitor, P of C1, we have 0 real part and minus 2.5 imaginary. What that means is that we have 2.5 bars, minus 2.5, meaning it's capacitive bars, minus 2.5 volt amperes reactive. For the current around the loop, we have, again, 50 plus J50 if we express it in rectangular form. For the power in the resistance, we have 2.5 plus J0. Of course, there is no imaginary reactive volt amperes. With the resistance, we have 2.5 watts of real power. And then for the source, we have to interpret this properly. It can be a little confusing. The reference in Multisim for power is a positive value, means power absorbed. So a negative value would represent power delivered. So we really have plus 2.5 watts of power delivered, but it's represented as minus 2.5 watts of power absorbed. And likewise, the imaginary or reactive power comes out with a positive sign here because it's using the convention of positive, meaning absorbed, but it's really delivering. So it would be delivering minus 2.5 bars. Now let's go back and look at this from the polar point of view. I'll go back and click on the grapher, single frequency AC analysis, but this time I'm going to change it to polar magnitude phase or polar form. We hit simulate, and now the two columns here read magnitude and phase. So as far as the input is concerned, it's still 100 at an angle 0. The output voltage, however, now gives us the magnitude is 70.7 volts at an angle of minus 45 degrees. The power associated with the capacitance is, again, reactive power. It's 2.5 at minus 90 degrees, meaning it's minus J 2.5. Reactive is minus 2.5 bars, volt amperes reactive. The current in the circuit is 70.7 milliamps at an angle of plus 45 degrees. The power associated with the resistance is 2.5 at an angle of 0, meaning it's real power. And for the source, we have 3.54 essentially at an angle of 135. Now, that again could be confusing because the positive reference is power absorbed. So this puts it in the second quadrant, but when you consider that we are really dealing with power delivered, you switch it around, and it's in the fourth quadrant would be a positive real part and a negative imaginary part, and that would give you the appropriate values for the power dissipated and the reactive volt amperes stored in the capacitance. So this concludes this particular presentation on single frequency AC analysis.